All right, let's jump right in. Today we're looking at something pretty amazing. It's basically a GPS for plant food. We're diving deep into this new model that shows us in crazy detail how a plant manages its nutrients, from the water it drinks all the way up to its newest leaves. So it really all comes down to one big question. How does a plant actually decide where to send its food? Think about it. It's constantly making these choices. Does this new leaf need more nitrogen? Are the roots okay on potassium? It's this whole internal logistics system, right? And figuring that out is the secret to growing healthier, stronger crops. And that's exactly what this model is built to do. Okay, so here's our game plan. First, we'll see how this model pulls two different ideas into one. Then we'll check out what's in the water. And after that, how nutrients actually get around inside the plant itself. We'll even follow a nutrient for a day in its life. And finally, we'll wrap up with why this is such a huge deal for the future of farming. All right, let's get into what makes this thing so special. See, in the past, scientists would usually look at what's in the water separately from what's going on inside the plant. Two different models, two different worlds. Well, this new approach completely changes the game. What it does is it takes those two separate ideas, the nutrient concentration and nutrient mobility, and smashes them together into one super powerful simulation. So you've got one model tracking the nutrient soup the plant's drinking, and another one figuring out how those nutrients get delivered internally. By putting them together, well, you get a much, much smarter and more complete picture of what a plant is thinking. So let's break down that first piece of the puzzle, the water. You can basically think of this part of the model as, analyzing the menu of all the food that's available for the plant to eat. Now, to do that, the model has to know everything about every single nutrient. And for that, it uses something called nutrient params. Honestly, the best way to think about it is like a digital ID card for each nutrient. It's got its name, its chemical form, exactly how much of it is in the water, all the key stats. And what's so cool is how specific this gets. It's not just guessing. For example, the model knows that every single nutrient changes the water's electrical conductivity, or EC, in a slightly different way. You can see here, the EC factor for potassium is different from calcium, which is different from iron. This incredible precision means the model knows exactly what's in that nutrient solution at any given moment. No guesswork. Okay, so we know what's on the menu. Now for the really fun part, the plant's internal delivery service. This is all about logistics. How do those nutrients get from point A, the roots, to point B, where they're needed most? And to really get a feel for this, let's actually follow a nutrient on its journey. The plant has this amazing internal highway system. But here's the catch. Not all nutrients have the same easy pass. Some get the express lane, others, not so much. And that brings us to a really key difference, mobility. You've got nutrients like nitrogen, which are highly mobile. If a new leaf needs some nitrogen, no problem. The plant can just grab it from an older leaf and send it over. But then you have something like calcium, which is poorly mobile. Once it gets delivered to a leaf, it's stuck there. It's basically locked in place. And understanding this difference is absolutely crucial if you want to predict when a plant might get sick. The model digs even deeper, linking a nutrient's mobility to how it travels. So you can see that the highly mobile guys, like nitrogen and potassium, use a bidirectional system. That means they can move up and down the plant. It's a two-way street. But our poorly mobile friend calcium, it's xylem-only. It can only travel up from the roots. It's a one-way ticket, no return trip. So where does the plant keep all this stuff? These nutrients aren't just floating around randomly. The model uses this idea called organ nutrient pools. It's a fancy term for a really simple idea. It's an inventory system that tracks what a nutrient's job is inside each part of the plant, whether it's a leaf, a stem, you name it. And this is pretty much what that inventory looks like in action. If you take just one nutrient, say nitrogen, in a single leaf, it's not all just one big pile. It's divided up into these different pools. You've got the metabolic pool for the day-to-day work, the storage pool for saving up, the transport pool that's packed and ready to ship out, and even a buffer pool for emergencies. It's amazing. The model is tracking all of this for every nutrient in every single part of the plant. Okay, now we get to see where the magic really happens. This is the dynamic part, where the model puts all the pieces together and simulates the thousands of tiny logistical decisions a plant is making every single day. So every single day in the simulation, the model runs through this four-step loop. First, it assesses needs. Which parts are growing? What are they asking for? Second, it checks supplies. Okay, what nutrients do we have available to send from older parts? Third, it routes the traffic. It calculates the absolute best, most efficient delivery routes. And finally, it updates the inventory across all those nutrient pools we just talked about. It's this constant, intelligent cycle. And the level of detail here is just wow. The model even factors in the weather. It uses something called a temperature Q10 factor to speed up or slow down transport. To put it simply, it knows that a plant's internal shipping network runs faster on a warm day and a bit slower on a cool one, just like it happens in the real world. So, we've got this beautiful, complex simulation running. But what's the point? Why does any of this actually matter? Let's bring this out of the computer and back to actual farms and crops. The applications are just massive. I mean, growers can use this to totally optimize their fertilizer use, which saves a ton of money and is way better for the environment. They could predict a nutrient deficiency before the plant even looks sick. You could develop perfectly customized nutrient recipes for any crop you can think of. It just makes everything more efficient, and it really paves the way for a future of smarter, more automated farming. And here's a perfect example of what that looks like. The model can actually calculate a hard number, like remobilization efficiency. For a highly mobile nutrient like nitrogen, that number is 80%. So what does that mean? It tells a grower that the plant can recycle 80% of the nitrogen from its old leaves to feed its new growth. Knowing a number like that is a total game changer for managing your resources. And really, that's the big takeaway here. This isn't just a bunch of code. By simulating this hidden world inside a plant, models like this one are giving us the tools to grow our food way more intelligently and sustainably than ever before. It's literally a digital blueprint for the future of food. And it leaves you wondering, right? What could we grow if every single plant had its own perfect personalized diet?